Okay, we gonna start this session by moving most of the our solved problem that been described in the previous clip to a new platform we call the Matlab. Okay, so we gonna show you and try to explain to you about this is the way that the program have been written. Okay, we have two files that we will discuss in this session. Okay, we certainly show you that the similarity of what we did with the in case of the Excel. This file we already explained to you. Okay, first we review what kind of problem we solve first. Okay, and as you know that the problem that we are solving, that we have originally we have a 6 decision variable and the coefficients of constraint matrix is have some uncertain condition. Okay, described in the first row. Okay, from column G to column L. Okay, in Excel. With this uncertainty, we generate what we call the 10,000 scenario. Okay, and we need to let's just say be able to balance the left hand side and right hand side with the constant right hand side of all 10 value, the value of 10. Okay, and this resulting in additional variable of u and v. Okay, and we already use open software to solve this, and also we also apply the Bender decomposition to solve this problem. Okay, and resulting to the final output here. Okay, so that's the platform for the Excel. Okay, but I think if you are familiar with Excel and you'll be able to write the program, it's okay, especially the VBA, that interface between Excel and the macro system, of Excel. Okay, you can go ahead and try to develop coding, based on this environment. Okay, and we already order an additional assignment that you can extend the number of scenario, keep extending the number of scenario, maybe more than 10,000, and based on statistic theory, you should be able to expect that the resulting target cell, objective function, of the problem, regardless of the number of constraints. If you have a really large sample, keep adding the sample, the scenario to the problem. I think that the resulting x, all 6 value of x and all the target cell of z, should approaching some certain optimum solution, in the population space, which in this case is infinite. You based upon the uncertainty definition here. But actually I think that we already discretize this, because of most of the number we round to with the precision of a 3 digit only. With a 3 digit. So we with this problem, both solving directly and using Bender decomposition, we can do it, under the new platform by using the coding called Matlab. Okay, and this is how the program look. Okay, and this is the first program. We call this a direct LP based on the example. Okay, we're gonna go a little bit explain for you a little bit that. Okay, for example here. Okay, we start the first line as with the command clear. Clear is mean that they will clear all the memory available and memory usage at that moment. So when you solve any problem, you start with this statement. Okay, so that you have the remaining available memory to utilize. Okay, and this is a tick, and this is a tick, and then it come with top or at the end here, tick top. Okay, this is a special command trying to uh, mark the time coming. Tick is mean that we start measuring the, the, the time usage. Okay, and then we once they reach the command stop. Okay, down here. Okay, it will measure the total time consuming from processing starting any command after tick and ending the last command before the top command. Okay, so this one I try to measure the time. N is a number of variable. In this case, it's 6. If you remember from the Excel file. M is the number of scenario. This is a 10,000 scenario. And NV is the number of total variable. As you know that when you have a 10,000 scenario, the total number of variable becomes 20,006, which come from 2 times M plus N here. Okay. And when you trying to solve this as a linear programming, you're gonna end up having to set what we call the matrix. Okay, you can recall this one going back to here. Okay, the original here. Okay, this is a matrix A here. Okay, matrix A over here. Okay, but in terms of direct formulation. Okay, this one is a direct example here. Okay, how come it cannot be? Okay, 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 here. A is the same as here. The matrix here. Okay, but I'm using this command because of the sparse matrix. Now the matrix A need to not only cover the A here, also need to cover the element of decision variable of U and V. Okay, so it will like A, I, and minus I here. Okay, so this is the same as we're trying to do on the Excel files. You might remember for each row I. Okay, from I equal 1 to M. Okay, the first 6 column is like this is a random number generator, the same formula that we use over here. Okay, the same as we use here. Okay, for example here the first row we have round. Okay, of this is we round the number of 1 plus random number times 1 with 3 digits. So this one is mean that you're going to end up having the value between 1 and at most is less than 2 with 3-digit value, with 3-digit precision. Okay, so in this one the same, right? We round 1 plus random, but this one is a random seed number 1. Okay, it's different from the Excel command. Okay, this is a Matlab command. And with the range only 1, so we don't need to multiply by 1. It's already automatically times 1. Okay, and with this comma with 3-digit precision. The same for the second, third, fourth, 5, 6. So all these 6 is the same as we generate in the first row here. Okay, and which had been randomly generated for our problem in 10,000 scenario. Okay, so after why we're using sparse here? Sparse is different. There's some alternative command. We might use a equal to zeros, CROS. Okay. If you use zeros, M and N V, it means that you have a matrix A, okay, with M column and NV, with M row and NV as a number of row and column respectively. Okay. If you use zero, it means that they will you are having what we call the dense matrix. Like you expect that all element within the matrix are non-zero constraint. But if you look at the original model here, okay, a huge number of zero contained in the I matrix that multiply U and the minus I matrix multiply V down here. Okay, so the resulting of the A matrix, okay, covering all decision variable, especially here, when in each row I, after n plus I is all equal to 1 and m plus n plus I equal to minus 0. The remaining element is all 0. When you consider that the number of non-zero element is much less than the number of zero element, in order for you to save the workspace, okay, save memory during the run, okay, you might replace this by using, instead of using zero, you replace with sparse. Okay, sparse is the opposition to dense. Okay, it means that you most of the remaining element we don't store it in the computer memory. We defaultly define them as a zero value. Okay. Okay, the same as the C matrix here. Okay, the C vector, sorry, C. This is all the cost value. We start that we have C equal to 0, NV, and 1. Okay, okay. And you know that you have, this is the number of variable. You have only one column here. This is, but most of the C value is non-zero. As you all know that the first 6 variable here is here. The same as here. This is all the cost element also, and this is for G and H for all each of G and V. Okay, so for all the first 6 element here, okay, okay, this is the original cost coefficient, and this is for each for G, Cn plus I, Cn plus M plus I equal to 1.5 divided by M. M is the number of scenario. 1.55 divided by M. So this is non dense, okay, not sparse. Okay, and then we set up L is as a lower bound for each decision variable with default is zeros, okay, for number of variable, and B is the right hand side, okay, vectors, okay, zeros and M, and then we all put the value of 10, okay, for all M, for all I, sorry. Okay, after that we reach the command top down here. So what we did here, okay, from here to here, okay, we just trying to generate the problem, okay, based on this form of formulation. Okay, so our cost in the objective function need to cover C, G, and H. Our original metric contain that link to all decision variable to contain A, I, and minus I, and right hand side of B. Okay, but all A we put it in the matrix, the constraint matrix A, and then we put all the cost coefficient to the C vectors, and we also put all the value of right hand side to the B vector. After that, okay, since this is equal, it's an equation, there's no inequalities, okay, so we are ready to run using the Matlab, which is a very easy command. Okay, you can see that at the end of this program, okay, we only tick and talk here. We try to compute the time over here. Okay, this is the object, okay, to solve for general linear programming. Okay, X will be the optimum, the same as here. The X contain X, U, and V. Okay, and then in Z is a objective function Z here. Okay, equal to, we call linproc. Linproc is a procedure object to solve linear with the C vectors. Okay, this one if we have any inequalities, you put it here, the left hand side and the right hand side. But this one, when you don't have that value, we replace it with just an empty blanket. Okay, the same as this is the right hand side, this is a constraint method. But we have equalities relationship equation here, a x is equal b here. Okay. And the lower limit of each decision variable is 0. Okay, the same as here, x u v greater than or equal to 0. Okay, so this one is just a really short, just one object, you solve everything. Okay, we'll see the application of this program later. Okay, along with this program, I already code another program for you. This is the same problem. Okay, you see that the same problem setting here, but this problem, instead of using the direct linear programming form, okay, I think that for the first couple line here, okay, this is a problem generation, the same as we seen, okay, in the previous direct solving LP code. Okay, but the difference start from this one. After this thing, this is the implementation, the coding for the idea of the Bender decomposition. Okay, so the Bender decomposition start here from this line. Okay, first of all, we only we don't need any NV anymore, just not like the direct model. Okay, okay, and you see that we change this. Okay, we don't need any extra storage for U and V. We only need the storage for A and only 6 variable. Okay, you might remember from the direct LP example here, over here. Okay, oh sorry, we need this to additional storage for here, and we have to set this as a sparse metric because of the sparse nature of this two input. Okay, but for this one, okay, we don't really need any extra column, especially the sparse column here. Okay, so we're saving a lot of memory here. Okay, and this is the original A, so and this is the original cost, but certainly we need to have this additional for the cost element, because UV can be easily trivially detected once you find X. Okay, but to evaluate the whole objective function, you still need this information, certainly, and also this one is the right hand side. Okay, and so your decision variable now only X, only N variable, and the original cost coefficient, okay, I'm gonna put it in the next vector, it's only we call CV. So CV have only N elements, okay, comparing to original C, which has a number of variables. Okay, so this is the initial setup, okay, for the before ending the process, and now we are trying to solve using the Bender decomposition. First of all, we identify the new objective function we call C of X, because if you might remember the Bender decomposition here, okay, we need to keep solving this problem again, and we have a new decision variable we call T here. Okay, T is like the additional column here, and the objective function have only one element, which is a coefficient is 1 according to the first variable, which is this one. There's only 1 multiply T. There's nothing related to X anymore, okay, in the objective function. So this is our objective coefficients, okay, the last setting of the process. And then we start computing the time for the Bender decomposition. First, okay, since this is a minimization problem, we identify C base, which is the optimum objective function, as a very large value at first. If we found a better solution, we keep replacing it until we get the minimum value. Okay, icon is a counting for the number of cut or the number of occasion, just like what we saw from the in the Excel file, that just like in this one in sheet 2 here, that icon, in this case icon will be equal to 80. Okay, we add 80 number of equation, and it also reflect the number of iteration, okay, happen during the dual the Bender decomposition. Okay, and this one we identify another variable we call gap, okay, equal to 1. Also a large, this is what we call the duality gap, the difference between the objective function and for the primal and the dual solution. Okay, and now we get into the loop routine. Okay, why the gap is still greater than, this is the accuracy to find whether the upper bound, the lower bound, the Bender decomposition approaching the optimum. Once it's less than 0.001, okay, which means the accuracy up to the first 3 digits, okay, we terminate. Okay, y is n here, okay, which means that we already get the approximated optimum solution. Okay, first of all, we compute this. We already identified b and ax here. Okay, so if you might remember, b minus ax is here, b minus ax here. Okay, this is just direct b minus ax. That's convenient for Matlab. And we identify the new y and u and v here. U and v is identified here. Okay, and this is the same as what we did over here. Okay, if you might remember, to find the y star. Okay, if we check b minus ax, if it's greater than or equal to 0, then assign the u of I, assign the u value, and assign the y value as the upper limit, and this is the y at the lower limit, and also the v have to be since b is less than 0, but v have to be non-negative, so it's a minus here. Once when b minus ax I is less than 0, v is minus of b minus ax at I element of the vector. Okay, so this is the way the loop that we are simulating what we did in this one to find the y star here. Okay, and this is also this is what happened here when we're trying to solve this sub problem. Okay, we check b minus ax. If it's positive, we put the g value, and if it's a negative, we put the minus h value. Okay, and also we assign the corresponding uv to the original model, and the objective function is here. Okay, this is the way we evaluate the objective function. Okay, we certainly will have CV transpose, which is the original first 6 variable of horse. Okay, and then okay, with this we accumulate with this one. This one is the same as G transpose U plus H transpose V. C transpose X is here. It's this one. Okay, and we check whether this is less than, you find a minimum value. As you might know, before we entering the loop, we set the C base as a very large positive number. Most likely it's gonna replace the O1. So C base is always the one that minimum solution that found in one of the iteration process, and X base is the optimum solution corresponding to C base. Okay, and now we're gonna go to the stage with that in here. We're trying to solve this equation. Okay, when you're trying to solve this equation, okay, we identify the coefficient first. Okay, this is y transpose A minus CV transpose. This is the same as what we did here, if you may remember what we did here. Find the element here, iteration by iteration. Okay, if you might remember from this one is that the coefficient corresponding to x is when we move to the left hand side is y transpose times A minus to the left hand side become positive, and minus C is that C is when moved to the left hand side minus C. So this is y transpose A minus C times x. Okay, so that's coefficient multiplied to x on the left hand side. So this is the one, y transpose. Okay, this is the notation of transpose. Okay, y transpose. Okay, times A minus C transpose. Okay, now you can have icon equal icon plus 1. Initially icon is 0. Okay, start to increase one by one in every loop that the while loop here is still working. Okay, so this one start the new constraint, and you know that the cut cons icon 1 equal to minus 1. Okay, the reason have to be minus 1 is that you now see that the cut con and right hand side cut here. You might remember from the old program that when we solve this directly with the model, it's all equation, but for this you have all inequalities. You don't have any equation, and the accepted form for the Lin-Proc routine. Okay, when you put the inequality in, they will accept just the relationship of less than or equal. Okay, so when it becomes less than or equal, it's reversed to here. Okay, so everything have to be reversed. The original left hand side here, you have to move to the other to the other side, and the right hand side also. So when you put this inequality to using the Lin-Proc command, okay, they can only accept the form of inequality of less than or equal. So all sign corresponding to the left hand side and the right hand side in this inequality have to change the sign, reverse the sign. This is how come. And you know that the same as t here. T, when they move to the left hand side, the coefficient multiplied to t in the constraint is 1. When moved to the the right hand side, to make it less than or equal, become minus t. This is why the coefficient of t here, okay, cut con at the very first column here have to be minus 1. And then for the next step, okay, for j plus 1, okay, when j equal 1, this is for all decision variable. Okay, this is just for the coefficient for t. Okay, remember that now your constraint become less than or equal. So this you have to reverse the sign here. This one is a coefficient j down here. Okay. Okay, you can see that the coefficient down here is get the result from this statement. Okay, so when you move, you want to enter the format of Matlab, you need to reverse the sign here. So all this just reverse the sign. And for the right hand side also, okay, the right hand side become you add the minus because you need to reverse the sign. So this is something different from what we did on the Excel here. Okay, so once you're ready here, okay, and you know that this command keep executing every time, and the cut con, okay, first at the very first iteration is only when icon is equal to 1 here, when you move here from icon 0 to equal. But iteration by iteration, an additional row will be added to the cut con here, and a row in every time this while loop has been executed. Okay, icon keep adding, automatically add a new row here, and make it, instead of just vector, start changing from vector to become a matrix. Okay, so this is a cut con, and then you have lower bound is 0, all 0. Now you need n plus 1 because you have an additional variable of t. Okay, so the right hand side. So the new one, the problem that you solve is over here. Okay, now you don't have any equation, so this one becomes just an empty bracket. And for inequality is here, less than or equal, and the objective function c of x, cx, okay, is setting up here. Okay, have only one objective function, just like what we did here, minimize t. So now you are ready to run. Okay, you can use the lin proc, just one statement here. You get the x new solution, and then you replace x new to x. Remember, when you replace it, you don't want to include the t variable here. So the xj, okay, you need x new from 2, 3, 4, 5, 6, 7. Because you're solving this problem, remember that you have a new additional variable of t. Okay, so when you move x new to x, you make sure that you make a right index matching. Okay, and the gap between this become the lower bound, and c base become the upper bound. The new gap is the difference between the upper bound and lower bound. And this loop of y, okay, keep repeating itself, okay, again and again until the precision required has achieved. Okay, so this is just a basic explanation of how do we develop solving the original model directly, and also trying to use when you apply Bender decomposition to solve this type of model. Okay, and in the next part, okay, we will show you when we apply this to program into the Matlab platform. Okay, see you.